Working with data that changes over time and across locations can feel very overwhelming, right? Spatial-temporal data aren't just numbers, they are like moving puzzle that tells powerful stories. In this tutorial, I'll show you how to make sense of this complexity step by step, so you can turn those messy multidimensional data into clear and actionable insights. So let's dive in. Hi there, I'm Joanie, your spatial data analyst. Have you ever worked with data that are all over the place, changing across time and location? If you do, you know how tricky it can get. Today, we're tackling exactly that kind of challenge with the carbon wire emission dataset, which is the dataset that was provided for the 21 week of 2024 for the Tidy Tuesday challenge. If you are wondering where to find those data, I will leave the link in the description below to my blog post where you can find all the information about the source of the data and the code I will show you today. So, this carbon dataset is packed with information about emission from companies around the globe, and it's the perfect playground for learning how to handle spatial-temporal data. Together, we'll first clean messy dimensional data, so it's ready to work with. After that, we're going to use a machine learning model to predict what might happen next. And lastly, we'll create a visualization that brings both the where and the when to life. Don't worry if it sounds a lot. I will walk you through every step so you can just see how powerful this type of analysis can be. Ready? Let's jump in. Okay, first let's load the tidyverse and my library, so it's just some utility function. The overall goal here is to predict carbon emission over time and space. But first we need to do some idea. We need to understand what kind of information we are dealing with, and we need to find and correct any bugs or errors that may affect our desired result. The first step in any IDA is to load the data. So here are our dataset. In this dataset, each data point has a year information, and the entity who produced the emission is identified in the column parent entity with an associated type, which can be investor-owned company, state-owned entity, or nation-state. The commodity column gives us the information about the source of emission. So we've got oil, natural gas, coal, or cement. The production quantity is identified here with its unit. And finally, the most important information for us is in the column total emission. This gives us the total emission traced to parent entity for a given year in million tons of carbon dioxide equivalent. Once the dataset is loaded, it's good practice to take a quick look at its structure and summary analysis. My favorite way to do it is to use the skim function in the skimr package. So here we have the information about the number of rows and the number of columns, and the skimr functions split our variable between character and numeric. In the character type variable here, we can see that there is no missing information, which is a gift, because in real life data, finding a way to deal with missing observation can be a really long and hard journey. What is interesting to notice here is the information about the numeric variable. So we can see that our emission dataset goes from 1973 up to 2022, with more information toward the ends though, so more recent information. And our total emission here goes from 8.8 ton to 8,000, a little bit more than 8,600 ton of carbon dioxide. Okay, For all the numeric variable, I'll also like to take a look in my IDA process at what kind of correlation we are working with. And to do so, Performance Analytic package has a really good function called chart correlation that gives us just that. So, here we can see exact same information that we had with the skim function, that we have more information for the recent years than the early 19 years. Apart from the distribution from each variable, this chart correlation function also gives us two more information. So we have the value of coefficient correlation for each 2x2 combination of our numeric variables, and its significance levels. So first, the correlation coefficient tells us about the strength and the direction of the linear relationship between two variables. So here, between year and production value, we have a positive, not so strong correlation between those two. Here, between production value and total emission, we have a much stronger positive correlation. Our significance level here is our p-value. So we have 3 stars for each combination of our variable. So this means that our p-value is between 0 and 0.001. So all that this means is that the significance level for us here tells us that there is sufficient evidence to conclude that there is a significant linear relationship between all our variables. So here, all that says is we can trust the correlation coefficient. Okay, now that we have a general understanding of our correlation, let's go look at them one by one. First, I'd like to see what is the general trend over time look like. So, to do just that, I need to take the dataset and group it by year. So here I have 169 group of my table. So we have 169 years. And if I want to see a trend over the year, I need to sum the value in the column that I'm interested with. So I need to summarize by total emission. So here is the data that we are going to visualize. One column for the year, so a table of 169 rows, and the sum of the total emission. To do this, we can just do a simple line plot, because the goal here is not to have a sophisticated graph, it's just to validate our understanding of the data. So here I want to see what kind of trend I have over time. The schema package and the chart correlation gives me a kind of an idea of this trend that I'm looking for, but the information was not summed by year. So here we are a little bit more precise. So here we can see some clear trend that the total emission get higher over time. And we make sure to sum our total emission values. Now let's take a look at the trend over space or over location. So if I want to know what kind of variation I have over location, I need to take my dataset and group it by parent entity. Here I have again my table, and it's grouped by 122 parent entity. The same thing goes here. We need to sum over total emission, and instead of a plot here, we can just go look at the table to see what kind of variation there is. So if I arrange my sum column from the lowest to the highest, we can see that each one of the 122 entity has its own emission value. We go from 105 ton to more than 76 to more than 276 ton of carbon. So now we have a trend over time. We look at the trend over space, so over location. What about the spatio-temporal trend? Let's focus here on the highest 6 emission entity. So our 6 entities that produce the more carbon emission are listed here. Started with China, which is the most important producer that we see just here. So all that is good. What if we filter our emission value to have just the emission of the top 6 producers? Here we have a dataset that contains only the 6 more important producers. And if we look at that with a plot, so we take our dataset that contains only the top 6, group it by parent entity and by year because we want a spatial temporal trend. We do exactly what we did for the 2 steps before, which is apply the sum on the total emission, because that's what we want to see. Here we have some variable type that we need to take care of. We need a date as a date and parent entity as a factor. To finally select only the variables that we need and pad by time. So it's just a little function from TyT that allows us to not have any missing year. So preparing the data and put it here. You got 6 time series plot with each graph representing one of our top 6 entities. So we see China here with its own trend. We see another one here with its own trend. What does that mean exactly? That means that every entity have its own trend over time. So that means that we are on the right path to predict our trend over space and time because we have some trend to predict. The next step here is to take a closer look at the data and see if there's some anomaly in them. Anomalies are unexpected deviation from the expected trend, so our blue line here, and outliers are extreme value that do not conform to the general distribution of the data. Identifying those 2 components is a crucial step for ensuring data quality, as they can distort statistical model and lead to inaccurate prediction. The package Anomalies here has a wonderful tool to do just that for time series. So here, if you want to detect anomalies using time series decomposition, we need a couple of functions of the Anomalies package. So we need to take our data. So we need to take our data here, plot data, which refer to here the emission of the top 6 entity with some housekeeping. And we need to apply 3 functions of the Anomalies package, so a time decomposition, an Anomalies, and a plot anomaly, which gives us this beautiful graph here on which each red dot represents something that could be an anomaly. So here our goal is to find out if these are really anomaly or not. And this is kind of a tricky question, especially where we can see a real seasonal pattern or some kind of trend. In a real-life situation, I will begin to find some kind of proof that every data that I replace the trend with is an anomaly. In short, better be safe and find a justification each time you make any changes on a dataset. And don't forget to keep track of those changes. In some cases like this one, the proof will be kind of hard to find. One way to approach this will be to create two models, one with the data set intact and one with all those outliers replaced with the general trend, and do the analysis of looking at the impact of the outlier on the performance of the predictive model. To keep things simple today, I will just replace those outliers by the general trend. Not because I have some kind of proof that they are in fact really anomalies, but just for educational purposes, simply because I want to show you how to do it. But don't forget to keep in mind that normally we should keep track of some kind of proof if you want to do this. Just before going to the next step, we have the package anomalies gives us another way to look at our data. So we can specify one of the entity that we want a closer look at, and we can apply the same two preprocessing components, some time decompose plus anomalize, and choose plot anomaly decomposition here instead of only choosing to plot anomaly. And we're having 4 other ways to view the values. So we have observed values, we have some kind of an attempt to plot seasons, which we don't have here because that's not the kind of a data set that works well with season trend. We have a trend here, and that kind of explains us why those red dots in the observed value are identified by the anomalies package as anomaly, because they're clearly out of the general trend here. And we got some reminders, so it's the difference between the two. That's just another way if you want a closer look to your data. So let's just jump in at the step where we remove the outliers. We look closely at the top 6 entity, but I want to continue my analysis with the top 50 entity. So instead of the top 6, I want the top 50. And since I changed the number of parent entity that I keep in my data, I need to go back to the raw dataset and apply exactly the same steps that we have been looking. But here I just choose to preprocess them all at the same time. Here, if you look closely, you saw that I remove some of the parent entity. I do that because further down in the analysis, those were some problematic entity in the dataset. Either they don't have enough data or they cause some kind of problem, and I don't want them in my top 50 because they will be absolutely impossible to predict. So here, our final data is composed of a parent entity in a factor format, a date, and an observed value, which is the sum of the total of the emission that we had in the raw dataset, corrected for the anomalies. Okay, now that we have a clean dataset to work with, it's time to start the modeling steps by some data preprocessing. Yes, more data preparation. There's always a ton of data preparation if you want a good model. So here we want to predict over space and time. I could have just done the modeling without the step that I present you here to use the GPS location of each entity. Probably in this case that won't have changed much because the result of the model of our study case here, because we are looking at only 50 locations over the world. So it's easy to assume that they are too far apart from each other to really have an influence on one another. But I want to create a map at the end of this, so I want to show you a proper way to create a spatial-temporal model. So we need some GPS coordinate. Before go looking for some coordinate, I need to associate my entity with the headquarters location. There are plenty of ways to do it. This time, because I had initially write this code for my blog in Quarto, I tested the Python integration. Once you have your environment set up, it really works like a charm. So I let you the code here so you can try it on your own. Basically, all this is doing is some web scraping in Wikidata. So this is a function. Let's go look in Wikidata to extract some kind of information about the headquarters. And you see here, even though I have this Python function to do some web scraping, I had to add some of the parent entity manually and I managed to find the headquarters location of each of this entity simply by going look at it in Google. So it's very easy, just I write the parent entity names followed by the word headquarters, and you should find some information to relate to some kind of headquarters location pretty quickly. And the last step is to go find the GPS coordinate of those headquarters. This one is an easy step that can be done with an air package, the register Google. So if you follow the step here, you can find exactly the link that leads you to the step where you can create your API, insert your key here so you can register ggmap with your Google API, and the ggmap function geocode let you extract the GPS location for each of your headquarters. So, just to save us some time, I already did those two steps, so I'm just going to load my data and join them, so we could have a final dataset that is composed of all the information that we previously had, so a date, an observed corrected value of an emission, the name of the parent entity, and the GPS coordinate. So, now that we have finally a complete dataset, we need to add one last step of preprocessing our data, and it's to create a spatial weight matrix. So we need some kind of information in our model to represent the concept of number of neighbors and or distance between points. There is many ways to achieve just that, and as I said before, in this particular example, the points are too far apart in space to have a significative influence on each other. But for educational purposes, let's try this concept with the key nearest neighbor weight. So to create our KNN weights, we need two functions. We need K near Nate and KNN2B. So let's start by creating that dataset with only the coordinate. So we extract the coordinate of our data final dataset, select only longitude and latitude, and create an SF object with it. Here. No, an XF object with relate. So let's run our two function from the SPDEP package, which gives us the K4 here because we have, for this example, set the key equal to 4. This means that each observation would get a list of the 4 closest points. Let's take a look at that K4 dataset. So this identifies the neighbors and this lists the weight. So we have here the neighbors and here the weight for each neighbor. And the last step here is to combine the two. With that done, the only thing that's left for us to do is to add those weights in the dataset. Which gave us our final dataset, which contains the date, the observed corrected value, our parent entity, and instead of the spatial coordinate, here we have a spatial weight. Here, our spatial dataset needs to be extended, nested, and splitted so we can create the model we need. To do that, we are going to need some function in the model temp package. So this data spatial need to be grouped by entity because it will be nested by entity. It's nested by entity because we want to predict a trend, a specific trend for each parent entity. We need to extend this time series. So extend the time series gives us the future length. So we are going to predict the next 20 years. This is going to be nested over parent entity. And this is going to be splitted also. So let's take a look at this. The nested data table is here. For each parent entity, we have a nested dataset that contains 139 rows of information. It's going to be our training dataset. This is going to be our testing dataset. So 20 rows of information are going to be useful for us to test our model trained on the actual data. And once we have a model that's performed good on the future data, we are going to predict 20 years in the future, so 20 years from 2022. Okay. To create the models, we need to load the TyT model library and create a receipt that tells the model that we are going to predict the observed value over everything else that there is in our dataset. And of course, the dataset that you need to look at is the nested data table, but first extract the train so you can train. But this recipe wouldn't be complete if we didn't add some more temporal trend in it. So we are going to add some step time series signature. I'm going to show you what this particular step does in just a minute. But first, our recipe also contains a step remove. So the date format, as we can see it here, is not useful if we have decomposed the time series. So this is going to be removed. We are going to add a step 0 variance on all predictors and dummy all nominal predictors. So if we run this recipe, that gives up a protocol in which every step that we add is listed here. But just for our training purposes, let's look at the data that will really be going in the model. So we've been keeping our spatial weight, our observed value, and here the time tk function step time series signature over our column date transform our date information here in many column that tries to understand what kind of seasonal trend there is. So we are going to add the year, add the year ISO, add the weekday, year, day, and many more other information. That's just a way to help the model understand what kind of trend there is over time. So, in time series, it is always a good thing to try many models at once and see visually which model perform well with which time series. So here we are going to use an XGBoost with a learning rate of 0.35, which will be our first model. The second model will be an XGBoost with a learn rate of 0.5, just to see how this is performing. And I try a non-giant thief, so a thief model, which will be our third model here. So let's run this in parallel. It usually takes 20 seconds to run, but as I'm recording this, it may take a little bit longer today. So this finished at 25.7 seconds, which is not bad. And it says that we have some errors. Don't worry, there is always errors in those kind of modeling situation. Let's look at them. So the extract nested error report, it's a function that's going to give us what kind of errors we have here. So we have error that says seasonal period M must be greater than 1. We have real can only be applied to numerator, not logical. The period argument could not be parsed. Okay. That's good. Also, we see the parent entity and the model name, in which there are errors, but that does not give me any kind of information about what is the actual error. So let's look at it some other way. So here, the table model time accuracy gives us another way to look at the predictive accuracy of all the models that were created. So here we have a bunch of null models, which probably are going to be in those that we see that were in errors right there. We have a bunch of models that had very high MAE, which is not good either. So let's look at this one. So if you want to see, if you want to investigate what it is that causing errors, you can try to extract the data. If we take a look at this China called parent entity, and we look at this forecast, we can see here that all three models were not really good at predicting the trend of our test data, so the last 20 years. So that explains why there is such an high MAE in our result table here. Okay, and if we look at British Coal Corporation, okay, British Coal Corporation probably hadn't had enough training data to predict a good test data. So this one isn't good either. So you see how you can look at the information that we have here, look at the errors that were listed there, and kind of understand by yourself which prediction you can trust or not. So I've done the work. I look at every aspect of it and I identify here that I need to remove some small time series. Once those that I didn't want to keep or remove, I can select the best model based on RMSE and extract the prediction on only some that I judge are the best predictive model here. So console energy was not bad, although former Soviet Union don't perform well either. So they look like they're the best, but we can clearly see that we add some modeling optimization to do. So it could be here to move around with the learn rate, find some kind of other algorithm that look like TIFF but perform a little bit different. So clearly in a real life situation it would need some work. But for today, let's move on to refit this, because our goal is to finalize, and there we go. We have the predicted next 20 years of the model that we had selected. Clearly not perfect, but it shows you how this is done. Okay, so the last step is to visualize our predicted results. So, the first thing to do when creating any kind of visual is to set a goal. What is the message that you want the reader to see firsthand? So, many visuals can be created here with those data. I chose to create an animated map, mainly because I never created one, so I wanted to give it a try. Here, I did not focus so much on the aesthetic of the map. I only wanted to create a simple map and see how I can manage the files to save a gift and use it on my blog. So we need some package to have first to animate our map and to have some kind of background that shows the world. In those packages, the word dataset here, that's how we access the world data that we can use to plot for plotting. Gonna load the data that we have just predicted, and let's go to the step where we are creating our map. So using ggplot and the geom_sf function, we are going to create the background for the map here. As I told you, I keep the color light, but I wanted kind of the drawing of the word so we can visually see where are our emission data point. On top of this, I'm going to use the geom_point function to just add our total emission here. Because we want an animated graph, we need to use the transition time function over our date column data. Adding the title here, carbon layer emission 4, and a little trick, we are going to use frame time inside bracket. So in the title of our plot, this is going to change representing the year on which we add the information. So you're gonna see just animated shadow mark. We are going to add a gradient. So I want my emission point to go from dark green, when they represent a low emission value, going to gold, yellow gold, where they are upgrading to a middle kind of emission, and go to a nearly reddish orange, where they represent a high emission. Some here plotting situation around the legend and the title on the axis, and the number of year where we are going to loop the graphing around is directly linked to the date that we add, so between the min and the max plus 1. So this code take a bit to run, so I had saved it on my computer, and here it is. So here it is. The data point appears slowly in order in which the data emission appear in our dataset, and the data points change in color and in size when the carbon emission in the dataset become higher. So we start with not much green, as we can see, but more a yellow color, and some point over here and over here turn brighter red once the year goes up and the emission goes up too. And there you have it, a complete walkthrough of how to tackle spatio-temporal data. From cleaning and exploring it to creating a stunning visualization and even build some predictive model. We turn a complex dataset into actionable insight, step by step. If you enjoyed this and want to go even deeper, I've got something special for you. I'm currently working on preparing some tutorials where I take the time to slow down and really explain every step in detail. I will cover everything from advanced technique, practical application, and even some behind-the-scenes tips to tackle real-world data challenge, including climate data, DEM, and I also plan to tackle some remote sensing data. I'll leave the link in the description below to subscribe to the waiting links. Thank you so much for watching. Don't forget to like, subscribe, and hit the bell so you never miss a new tutorial. Let me know in the comments below what kind of project you love to see next. See you soon!